Okay, greetings internets. Today we're going to finish off the topic 5.2 handout number 2 that I started and then did not finish because I had a meeting. And also because the rest of this is going to take a little bit of time. So let's take a look. So this is our circuit. And as you can see, there are a couple of interesting features here. The main unique feature of this circuit is the fact that our parallel circuit component has a couple of resistors or light bulbs in series. Okay, so we'll talk about how to deal with that in a second. Then we also have the parallel component here and another series component here. So we're really mixing it up now. So we're first asked to determine the power in each lamp, and these all have the same resistance. So I'm just going to call each resistor R from this point forward, and it makes life a little bit easier. Okay, so the first thing I want to do is find my parallel resistance. And the way that I do that is by doing this. So notice here that we have combined the series resistance from our series component so that we have a total resistance from this point to this point of 120 ohms. Okay, so that is the value that we put in for our initial inverse parallel value right here. Okay, so we then add our other parallel component, which is just 1 divided by 60 ohms. And we take the inverse of that total quantity, and we get a total resistance of 40 ohms. So our parallel resistance is equal to 40 ohms. Okay, we're then going to add that to our component in series with the parallel resistance, bulb D. And we will find that our total resistance through the entire circuit is now 100 ohms. And from this point, we calculate our current through the entire circuit, which is going to be 0.3 amps. Okay, so this is usually the sequence of moves that you will take when you start analyzing a circuit. So start with parallel resistance, add that parallel resistance to any components that are in series with the parallel resistors, and you'll get your total resistance for the circuit. Okay, so moving on. We need to find the power through each lamp. Okay, so we're going to start with A and B. And for A and B, what I've done here is I've calculated the voltage across these parallel components here, so V sub P. And there are different ways that you could do this. You could also use Kirchhoff's law for current to calculate the current to each component. But I've just taken, so you could use Kirchhoff's law for current there. I've just taken the voltage because it's going to be the same for the top and bottom, and it's therefore a little bit easier to deal with. But again, 6 of one, half a dozen of the other. It doesn't really matter how you decide to go through it. Okay, so for A and B, our total resistance is going to be 120 ohms. Our total power is going to be the voltage divided by 100, the voltage squared, divided by 120 ohms, and that's going to give us 1.2 watts. So the total power across both A and B is 1.2 watts. And that is going to be divided between each series component. Okay, so we divide 1.2 watts by half, and we get 0.6 watts. Okay, the only reason we can do this is because they have the same resistance. If their resistances were different, then things get slightly trickier. We just have to allocate a proportionate amount of power to each resistor. All right, for resistor C, then we have 12 volts squared divided by 60 ohms, 2.4 watts. Okay, and for resistor D, here I'm just going to use the current. So the power through D is going to equal the current squared times resistance, and that will be 5.4 watts. Okay, note that I've done a quick check here, and I really recommend that you do this because it's just a good way to make sure that you're making the right moves. If you add up all the power in the circuit, it should be equal to the power coming out of the battery, which I've calculated right here. Okay. You could also use the current through the battery times the voltage, and that would be fine as well. So there are just multiple ways that you can check this really quickly. Okay, so if A burns out, then current cannot flow through either A or B. So let's take a look. So lamp 8 burns out, and what that means here is that we have a broken circuit here. So where this once was a whole and functional circuit through this loop, we're now not going to have any current flowing through this part of the circuit. So what that means is if I hook up a voltmeter to this point and try to measure the voltage across lamp A, what I'm actually going to be measuring is the voltage across lamp C, okay? And the reason for that is because the wires of this lamp will now just act as a normal wire, okay? So it's not going to be getting any power because the circuit is broken. Okay, so I had a question about that, and hopefully that explanation makes sense. Okay, so current cannot flow through A or B, so the power to each of those is going to be 0. If you wanted to be really picky, you might say that they were that lamp B would be consuming a very tiny amount of current because it's still going to have a tiny amount of resistance. Okay, but generally we just assume that it has 0 resistance in this case. All right, I sub 0. Last one. All right, so we're looking now at the power across D and C, and these are now just in series. Okay, so D and C are going to be series to each other because this is no longer a parallel component. It's now a series, just a full-on series circuit. Okay, so what I've done is calculated the current through the entire circuit, through each series component, and then use current squared times voltage. And again, there are multiple ways that you could approach this. I'm not sure what the book did, but it wouldn't surprise me at all if it were different. Okay, so there you go. All right, so we've talked about 5.16. Let's go on to 5.17. The EMF of the cell is 9.00 volts. Internal resistor, as is often the case here, is assumed to be negligible. A non-ideal voltmeter with resistance of 500 kiloohms is connected in parallel to a resistor of 500 kiloohms. Okay, so determine the reading of the ideal ammeter, and that will mean that the ideal ammeter has 0 resistance. So when we're talking about ideal ammeters and voltmeters, the ideal voltmeter has infinite resistance, and the ideal ammeter has 0 resistance. And of course, there's no such thing. In both cases, your ammeter and voltmeter are not going to have either infinite or 0 resistance. So be aware of that. But generally, unless the problem says otherwise, you will assume that they're ideal. Okay, so the first thing we need to do is find total resistance to the circuit, which I have done here. So total resistance is equal to 250 kilo ohms. And we then find our current through the circuit, which is quite small, as we would expect for a resistance that large. 3.6 times 10 to the negative 5 amperes. So that is part A. Estimate the resistance a student would calculate if he were to use a current found in A. Okay, so we've already calculated the apparent resistance in the circuit, and it was 250 kilo ohms, so there you go. No reason to repeat our work. Finally, in this circuit, the battery has an EMF and a negligible internal resistance. Derive an expression for the voltage V sub 1 across resistor R sub 1 and the voltage V sub 2 across resistor R sub 2, and it just looks like this. So we take our equation, and this is straight out of your data booklet. We take our equation for EMF, which is equal to current times the internal resistance plus the resistance of the circuit, and we rearrange it slightly. Okay, and then we find V sub 1 and V sub 2 just using some basic algebra, as you can see here. Okay, so that's it. Again, if you have any questions, please don't hesitate to let me know. Drop me an email or smoke signal or telepathy. No, not telepathy, but email and smoke signals are good. Okay, have a great day.